Welcome to our exploration of human skeletal muscle biomechanics. In this video, we'll uncover how skeletal muscles work together to produce the coordinated movements that allow us to walk, run, and perform daily activities. Understanding these mechanisms is crucial for students, athletes, and anyone interested in how the body functions. We'll start by introducing the basic principles of muscle function and gradually dive deeper into the science behind movement. Let's set the stage for a fascinating journey into the world of biomechanics, where physics meets biology to explain the marvel of human motion. Skeletal muscles are the engines of movement in our bodies. They attach to bones and through contraction generate the forces needed to move our skeleton. But how do these muscles actually produce movement? It all comes down to the interaction between muscle force and the joints they act upon. When a muscle contracts, it pulls on the bone, creating a force that results in movement. This process is not random. It's highly coordinated and relies on precise control from the nervous system. Let's take a closer look at how this force is generated and transmitted. Key concept in biomechanics is torque, which is the rotational force produced by muscle at a joint. Torque, often represented as Tm, is the product of the muscle force Fm and the muscle moment arm d perpendicular. The moment arm is the distance from the joint center to the line of action of the muscle force. This relationship determines how effectively a muscle can rotate a joint. The longer the moment arm, the greater the torque for a given muscle force. This principle is fundamental in understanding how muscles move our limbs efficiently and powerfully. Muscle force generation depends on the recruitment of motor units. A motor unit consists of a motor neuron and all the muscle fibers it innervates. Not all motor units are activated at once. Instead, the body recruits them based on the force, speed, or duration required for a task. This recruitment process is highly organized and follows a specific order, ensuring smooth and efficient movement. Understanding how motor units are activated helps explain why some movements are gentle and others are powerful. One of the most important concepts in muscle physiology is Henman's size principle. This principle states that smaller slow-twitch motor units are recruited first because they are easier to activate. As the demand for force, speed, or duration increases, larger fast-twitch motor units with higher thresholds are progressively recruited. This orderly recruitment ensures that movements start smoothly and become more powerful only when necessary, optimizing both efficiency and control. Let's compare the two main types of muscle fibers, slow-twitch and fast-twitch. Slow-twitch fibers are associated with smaller motor neurons. They are easier to activate, have slower conduction speeds, and are highly resistant to fatigue. These fibers are perfect for endurance activities like maintaining posture or walking. On the other hand, fast-twitch fibers are linked to larger motor neurons, are harder to activate, and can generate much more force, but they fatigue quickly. These are the fibers you rely on for sprinting, jumping, or heavy lifting. Activation thresholds play a crucial role in muscle function. Smaller motor units with slow-twitch fibers have low activation thresholds, meaning they are recruited first and with less effort. As the activity becomes more demanding, the body recruits larger motor units with fast-twitch fibers, which have higher thresholds. This system allows for precise control during light activities and the ability to generate large forces when needed, such as during intense exercise or lifting heavy objects. As you increase the force, speed, or duration of an activity, your body progressively recruits more motor units. This means that during a gentle movement, only a few small motor units are active. As the demand rises, larger and more powerful motor units join in. This progressive recruitment ensures that your muscles can handle a wide range of activities, from delicate tasks like writing to explosive actions like jumping. Better understand how motor units are activated, let's look at a visual representation. Imagine a graph where the smallest motor units are activated first, followed by progressively larger ones as the need for force increases. This visualization helps clarify why movements start gently and only become forceful when necessary, protecting muscles from fatigue and injury while maximizing efficiency. Small motor neurons, which innervate slow-twitch fibers, are designed for endurance. They have thin axons and fewer branches, making them easy to activate and energy efficient. These neurons are perfect for activities that require sustained low-level force, such as maintaining posture or walking for long periods. Their resistance to fatigue means they can keep working without tiring quickly, supporting our daily movements seamlessly. Contrast, large motor neurons control fast-twitch fibers. These neurons have thick axons and many branches, allowing them to activate many muscle fibers at once. They are harder to activate but can generate high force rapidly. However, they fatigue quickly, making them suitable for short bursts of intense activity like sprinting, jumping, or lifting heavy weights. This specialization allows our muscles to adapt to a wide range of physical demand. Energy efficiency is a key difference between slow-twitch and fast-twitch fibers. Slow-twitch fibers use energy sparingly and are built for endurance, while fast-twitch fibers consume more energy and tire quickly. This distinction is why marathon runners rely on slow-twitch fibers, while sprinters depend on fast-twitch fibers for explosive speed. The body's ability to switch between these fiber types is essential for adapting to different physical activity. Let's apply these concepts to real life. When you stand or walk, your body primarily uses slow-twitch fibers, which are efficient and fatigue-resistant. But when you need to sprint, jump, or lift something heavy, your body quickly recruits fast-twitch fibers to generate the necessary force. This seamless transition between fiber types allows us to perform a wide variety of movements, from gentle to powerful, all coordinated by the nervous system. Visual aids can help us better understand the differences between small and large motor neurons. Diagrams and illustrations show how thin slow-twitch fibers are organized for endurance, while thick, fast-twitch fibers are structured for power. These visuals reinforce the idea that muscle structure is closely linked to function, and that our bodies are designed for both stamina and strength, depending on the demands placed upon them. Summary: the biomechanics of human skeletal muscle involve a complex interplay between muscle force, torque, and motor unit recruitment. Henneman's size principle ensures that movements are smooth and efficient, starting with slow twitch fibers for endurance and progressing to fast twitch fibers for power. Understanding these principles helps us appreciate the remarkable adaptability of our muscles and the sophisticated control systems that govern our every move. Whether you're an athlete, student, or simply curious about the human body, these insights reveal the incredible design behind our everyday actions.